Hello everyone, we are from Tokyo Metropolitan University and Entity Communications. Here we present our research shuttlecock detection using residual learning in unit architecture. This is the outline for the presentation. From the introduction, related works, method, experiment and results, conclusion, and the last is references. Badminton is the fastest racket sport in the world, faster than ping pong, faster than tennis, and faster than squash. In fact, it's even faster than a golf. This makes badminton not only exciting to play, but also incredibly exciting to watch. It keeps players engaged with the game because everyone on the court needs to stay aware and ready for the next shot. Every single person's badminton play style is unique, while play styles may be similar and broadly categorized into something like control, attack, or defense oriented. Players ultimately make up their own unique overall play style. This wide variety makes for interesting and fresh gameplay as you play badminton each time. Badminton is considered the second most popular sport worldwide after soccer. In tactical analysis of the badminton, shuttlecock trajectory provides essential information in order to compute hitting timings and other shot parameters. Therefore, extracting shuttlecock trajectory information from recorded badminton is a highly demand. And several existing works on shuttlecock detection have been proposed. It was TrackNet V2 by Sun et al. In 2020. And due to the depth of the network, TrackNet V2 might suffer a well-known vanishing gradient problem. Then we believe there is a room for the architecture of TrackNet V2 to further improve the shuttlecock detection performance. We propose to extend TrackNet V2 by introducing residual connections in its blocks. So a residual connection could mitigate the gradient vanishing problem, resulting in a higher shuttlecock detection performance. So TrackNet V2 was proposed to detect the shuttlecock from badminton broadcast match videos. It consists of a unit-based encoder-decoder backbone. So you can see there is no skip connection within any convolutional block which could prevent vanishing gradient during training. So this observation motivates us to introduce residual learning framework to TrackNet V2. And how about a residual network? So recent research has found that a deeper network could achieve better performance, but training such deeper networks become more and more challenging due to the well-known gradient vanishing problem. A researcher proposed the deep residual learning framework, which used identity mapping to make training easier. So there is a formula behind the residual learning of the group stack layers, where each layer is specified as formula that you can see. The Y is the output, and this is the formula of the residual learning. So this is the method that we propose. So this is the table of the convolutional block. There are many block here. So from the input until the output, and inside there is an encoder and decoder, and we divide every encoder is 3 and decoder is 3. And if we want to look at the detailed visualization of an encoder block, this is the encoder block in our proposed model. And the below is the detailed visualization of a decoder block in our proposed model. So decoder block here has many blocks than the encoder block. So about performance term detail, there is a negative and positive. So the precision is the ratio of the true positive over the sum of false positive and true negative. And a recall is the ratio of the correctly predicted outcomes to all prediction. And the accuracy is the ratio of the correct prediction out of all prediction made by an algorithm. So this is the performance term that we will use. So the other method is we change bilinear upsampling to transpose convolution. Why we change the bilinear upsampling? Because when we use a bilinear upsampling, when we move to the second training and the third training, the result is different between the first, second, and the third. But if we change the bilinear upsampling to the transpose convolution, the result will be same. So we can continue to the research. So this is the overall network layer detail of the shuttlecock detection system with the additional of residual function. So you can see there is a residual function here in every block, here, in every layer. So this is our proposed method to make a shuttlecock detection better. In the experiment and result, we use a dataset from shuttlecock trajectory dataset, and this is the example frames in the shuttlecock detection dataset. There are many broadcast match video of the badminton, and this is the example frame in the shuttlecock detection for a testing data. So this is for training and this is for testing. And this is the training details of the experiment, and in the inference, and there is a training loss and validation loss, and the red one is our proposed method and the blue one is the truncated v2. You can see the loss is lower than the truncated v2, and the validation loss too, we can get a better loss in here. This is the final result of our proposed shuttlecock detection method. You can see there is a truncated v2 result and our proposed method result. In the precision, recall, F1, and accuracy, our method has a better result than the truncated v2. So in the experiment, you can see in the A is a truncated v2 and the B is our proposed method. So the red dot is a ground truth and the green dot is the prediction. This is a red dot here, here, and the green dot is in here. In the truncated v2, they wrong or misdetection of the shuttlecock, but our proposed method works better than the truncated v2. So in the conclusion, we propose a shuttlecock detection network that integrates residual learning to unit-based truncated v2 model, and our proposed method performs better than truncated v2. It improves precision, recall, F1, and accuracy in all aspects. So this is our main references of this research. Thank you so much.